So once again, I thank you for having me at this conference. It's actually learned quite a bit. I'll talk about the fluorescence of a small Josephson junction and a possible relation to so-called Schmid transition. I'll tell what is it. I'll remind what is it. So it's a theory work that we did when I was there, mostly long distance during the shutdowns, and there is also a combination of this experiment which was inspired by our theory to some extent. So here's the outline. So I'll remind what is Schmid transition first in a shunted junction. Then we'll do another representation of Schmid transition in the context of circuit QED. And it actually leads us to a new quantum impurity model. Then we'll discuss what are the signatures of Schmid transition in the inelastic differential cross-section for the photon scattering. And lastly, I'll tell a little bit about experiment and the theory. An experiment addressed so far only the total cross-section, which is a much simpler quantity. So let's start with a single junction, single small Josephson junction between two superconducting islands. So the second term here is just Josephson energy, and we are interested now in energies which are much less than the gap in the least of the junction. So the only variable, dynamical variable here is phase, and the second term is conventional Josephson energy. The first term is just the charging energy, and it corresponds to a certain number of Cooper pairs transferred, say, from left to right. Okay, so 1 over I dd phi is transferred charge, and this thing is nothing but just classical charging energy. EC tilde is E squared over 2C tilde, where C tilde is a junction's capacitance. So it's a very simple Hamiltonian, like 1D tight binding or 1D crystal problem. And indeed, in case of tight binding, you can think of rare tunneling events of phase between the minima, 0 to pi, and so on. So height of the potential here is J, and inverse mass is EC tilde. So if this ratio is large, then these tunnelings are rare, the amplitude is small. Nevertheless, the phase is delocalized. So the correlation, if I start with some phase, it will diffuse away, quantum diffuse away. So the core function of phi of t, phi of 0, tends to infinity at large times. And it means that it's not a superconducting system. In a way, it's an insulator. And indeed, if you just apply external electric field at low frequencies, you have only polarization. There is no current. So there is no inductive response. It's just polarization like in a molecule. It's like a small piece of dielectric. So despite being made of superconductors, the system actually is in insulating phase. Now, we can slightly modify the formulation, introducing also a polarization charge induced by some external source. So it's purely Hamiltonian thing. There are no dissipation involved. And basically, polarization charge corresponds to change of the boundary condition for the wave function. It's Aronoff-Kasher effect. So when I change phi by 2 pi, the wave function accumulates additional phase factor e to 2 pi n, where n is the polarization charge induced by external, say, battery. And again, it's a tight binding model in elementary solid state, and you'll get for the lowest band in tight binding like a sign dependence on n, which is charge, and the counterpart in solid state is quasi momentum. And in this pictorial presentation, basically every time phase tunnels between minima, there is a winding of the wave function by e to 2 pi n. So static polarization obviously doesn't change the fact that the phase is delocalized. That remains true. Now the question is that suppose that this polarization charge is not induced by a battery and capacitors, but somehow a dynamical variable of the environment. Okay, and the question is whether if it's a dynamical variable, it may affect the behavior of the phase and maybe localize the phase. The inspiration for this question comes actually from a Kavli model that was developed in connection with MQT tunneling quite long time ago. So this is a piece of their paper, and basically the environment was modeled by a bunch of harmonic oscillators, which are coupled in a linear way to the variable of our system, to coordinate q. And basically, this bunch of oscillators can be viewed as a spectrum of one-dimensional liquid, Latinger liquid, if you wish, in some auxiliary dimension labeled by S. Okay, so you have some axis in some strange space where this liquid lives and produces a spectrum of the excitations that is in yellow here. The coupling, the last term, corresponds to coupling of our system's variable Q to the variable of the environment. In this case, it's pi hat density of momentum at point S equals 0, at one point. Okay, so there is some string in auxiliary space that is attached to our particle, and basically when the particle tries to tunnel, it excites the string, but also there is some back action, and it may affect the dynamics of the particle. That was the idea. Now, there was a generalization on the case of periodic potential instead of this guy kind of an equilibrium situation with like a sign potential. It was done in a number of papers which are listed here. And basically, that corresponds to n hat introduced on the previous slide, to replace n hat by basically a parameter or variable proportional to theta hat, where theta again is a variable of our 1D, if you wish, Latinger liquid, but purely harmonic Latinger liquid. Nothing. I mean, there are no any cosines. It's just a harmonic system, a string. So, what this coupling leads to? If lambda is 0, so no coupling, we just discussed. Say, if I look at the lowest band in this tight binding potential, the band has a finite width, and this is WKB expression for the width. Now, introduction of the dissipation of the environment actually makes band more narrow. This exponent alpha is proportional to lambda squared, and there is a critical value of alpha equals 1, when the bandwidth just collapses. Okay, so the collapse of the band actually corresponds to the system becomes superconducting, because collapse of the band means that the phase will be localized. Now, this model was developed in order to describe shunting of a junction by a normal state wire resistor. In a crudest assumption that basically this resistor is purely classical, despite being almost at zero temperature. So no weak localization. Just what happens, what is assumed is that this variable theta hat, roughly speaking, just creates excitations, bosons, which are particle Hall pairs. Well, I mean, of course, particle pair is not exactly boson, but let's forget about the small differences. So that was the idea behind the Kavli model. And in this rendition, which is more real, parameter alpha actually is inversely proportional to the resistance of this resistor. I call this resistance for now capital Z. Okay, RQ is a quantum unit of the resistance here. So once again, when charge dispersion is collapses, and that happens at small resistance of the shunt. So if I reduce the resistance Z, then at Z less than critical value, this formula is not applicable anymore. Basically, epsilon tilde becomes 0. Okay, so charge does not fluctuate. Yes, sorry, the bandwidth of the charge becomes 0, and that corresponds to full localization of phase, right? So the tunnelings between the minima for the phase are just prohibited, because basically epsilon naught tilde is the amplitude of tunneling for the phase from one minimum to another. So if epsilon naught tilde is 0, no tunneling, phase is fixed. So we start at some phase, say equals to pi n, and it stays there forever. Fluctuations are less than pi. Again, if you think of it, it's a non-trivial thing. So in ideal system, isolated system, okay, just this guy without any leads attached, it has purely dissipative shunt, okay, so 0 omega is flat as a function of omega. And we are telling that at low frequencies, it should have a purely inductive response. So, okay, so if phase is not fluctuating, then in response to external AC field, it should have 1 over I omega current response. So it's purely inductive. So it's pretty bizarre statement. People try to check it, and most experience were in DC regime and measure differential conductance, which is not exactly the system. And I would say that in some way, the Schmid transition existence is still somewhat controversial, and I will not go through these papers just to flash that. Two very respectable and very clever groups of experimentalists have diverging opinions about it, and there is some back and forth. So the question is that is there some other way to approach Schmid transition? And actually, talking to Vlad Manucheran at Maryland, here's an idea. So in the circuit QED context, one might try to replace the resistor by a transmission line made of many Josephson junctions. They are small junctions, okay, but it's a infinitely for series long line that allows propagation of photons, or actually plasmons, which take the role of these bosons. So they are replacing now the particle pairs in the resistor, which is kind of a more murky subject, more object. So this is our resistor, and I will call the small junction by its real name, Transmon. And basically, the Transmon is very Hamiltonian, with the condition that EJ tilde is much larger than EC tilde, which you want to use anyway, right? So that means that the potential is rather deep. And it means that there are many, well, actually several, better to say, narrow bands that this potential supports. And say between two lowest bands, the difference of energies, if I just replace bands by straight lines, is so-called Josephson plasma frequency squared EJ EC. And people usually make devices in such a way that this frequency is accessible by microwaves. I know it's about 4 gigahertz, so it's relatively easily to access by microwaves. Now, but again, if this ratio is large but not too large, there is appreciable width of the bands, and the higher the band, the larger the width. So this E1 to E0 is a large parameter. And actually, it's numerical also not so small. It's I don't remember. The experiment was about 20, I think. So now, what about our resistor or the chain? Okay, it's basically it's a chain of junctions, and in this lab it was like 20 or 30,000 junctions. So it's really long chain. The spectrum of plasmons, okay, saturates, of course, at large wave vectors, so that the wavelength is order of the distance between the two junctions. But at small wave vectors, it's pretty linear, actually. It's very linear. And if we, and basically, that's the part of spectrum we want to use. Now, where is the Transmon attached? It will be attached here at this end of the transmission line. Okay, and Transmon sees the impedance of this line, Z of omega, and this impedance is indeed purely dissipative. If we are within this linear part of spectrum, it's just given by a square root of the capacitance energy, where Cg is capacitance of an island to the ground, not between the islands, but to the ground. That's important. And Ej, the Josephson energy. Now, again, jumping ahead, I would say that Z in experiments was actually larger than the quantum unity, which is also kind of an achievement to make the impedance of a transmission line larger than quantum squared over H. But when you start with in vacuum, it's 100 times smaller, right? So it's speed of light. Okay. Fine. So now, so in terms of light liquid, there's parameter, quantum parameter k, which is scale is 1 over z. So if I translate what was in Schmid transition in terms of capital K, then we expect that at k equals 1/2, the bandwidth collapses, and then one must have a superconducting response of the Transmon. Now, a new tweak is that there is a new probe. One can look at a photon that comes in, with resonant frequency, and we can look at photons that come out actually at smaller frequencies. And because of nonlinearity of the Transmon, this process is possible. Okay, so there is not only the elastic backscattering of a photon, but also an elastic one when one photon with energy h bar omega creates outgoing photons with sum of energies h bar omega, but the number of photons may be larger than 1. The smallest number actually is 3 because of time reversal. So basically, one can look at fluorescence spectrum, and what we claim that fluorescence spectrum actually carries information about the Schmid transition. So now I want to take a, well, there's not much time left. There's a minute of pride. So it's a kind of a new quantum impurity problem. Let's maybe go to different gauge and transform capital N from the boundary conditions into the Hamiltonian form. Okay, so if I just do change the variables, I can put n script n under the square here, right? And basically, what we are telling is that if we use this gauge, and now instead of the external fixed, and instead of the polarization induced by some external, capacitor, we introduce a galvanic connection to the transmission line. This n script is replaced by n hat. This n hat is the charge induced by plasmons on the Transmon. Okay, so that's the idea. So n becomes n hat as we want, and it's this n hat is basically produced by fluctuations of the plasmon fields. And it's a generalization of Sine-Gordon model in the sense that the boundary now carries some internal degree of freedom, which is this Transmon level structure, which is not so simple, and there are infinite number of levels at fixed n. So it's a new rendition of Sine-Gordon. It's more it's more complicated. Now, okay, so now basically I'll tell the crux of the calculation. So basically, why inelastic process is possible? There are kind of two origins of the splitting of a photon on several outgoing photons. One is the classical anharmonic effect. Cosine phi is not phi squared, right? And that allows a classical nonlinearity which splits the incoming light into harmonics, subharmonics actually. And there is another mechanism which is specific for the system. Is I would say quantum phase slip mechanism. So again, I will not go into detail, but basically here is this Hamiltonian with the classical displacement charge. Okay, and we know that it produces a spectrum of bands which are cosine n bands with different prefactors depending on the band number, 0, 1, and so on. They're getting wider when you go up. And basically what we do is like pile substitution. This script n is replaced by an operator. Okay, so basically this chain of Josephson junctions supports plasmons, and these plasmons produce a back action onto the Transmon. So this back action is important, and that actually allows for the phase lifts to interact with plasmons in the array. Basically, with photons, and this interaction is highly nonlinear. And one can show, actually, one can go to, I mean, it's a tedious calculation, but one can look at 4-photon process, so basically the lowest process, and look what phase lifts do, and look for the classical anharmonicity does. And the difference is drastic, because for soft inelastic transitions at small omega minus omega prime, the phase lifts produce divergent contribution to the inelastic differential cross-section, whereas the anharmonicity is quite benign. So now we concentrate on the phase slips. We forget about harmonicity, and then we go full strength. So what we can do analytically is to do lowest order in the phase slips amplitude, but sum over all the orders in capital K. So basically over all the orders in the photon multiplication number. We integrate over all low energy photons and concentrate on small differences between the incoming omega 0 frequency and outgoing frequency omega prime. Okay, so there are also this shower of photons going out at low frequencies. We just iterate, we don't catch them, so they go away, and we just iterate over them. So the inelastic scattering is a function of omega 0 and omega prime. It's differential cross section, scales as a power law. It depends on capital K, and there are two important things, and I'm almost done. So one thing is that at K less than 1/2, actually, this cross section is not normalizable. So one has to, go to small omega prime minus omega 0 and do more careful job and to regularize it. But the fact that it's not normalizable actually is an indication that the phase fluctuations are strong, and it's an insulating phase. And there is actually, if you look carefully through this Guinea paper, there is some counterpart, just mathematical counterpart of this object that now becomes physically accessible. Now, at critical point, there is a value of this critical exponent, -1. And basically, that is, we claim, would be a manifestation of the Schmid transition. So this is, so far, is beyond the experiment. So what was done in the experiment actually is a measurement of the total cross-section. Okay, so we iterate over omega prime as well. And as I said, it requires additional theory job. And the result is that the total cross-section scales as the resonant frequency to power 4K. And that's when which runs basically data. So the points here are data for 4 different devices. They all had K less than 1/2. Now the stripes, I wish it would be lines, but it's stripes because this parameter epsilon1, the phase slip parameter, is hard to tease out from independent experiments. And the uncertainty in epsilon1 basically brings the uncertainty that gives us stripe bits. But there is a, I would say, reasonable agreement, relatively reasonable agreement with the theory. And actually, if we are going deeper in the insulating regime, so K small, this correspondence is better than at K closer to the transition into the superconducting state. So basically, that's all the story I wanted to tell. So to conclude, there is a new type of quantum impurity model, which is generalization of Sine-Gordon Hamiltonian. The phase slips actually turned out to be a very effective mechanism of soft inelastic photon scattering of this quantum impurity. Now, what would be interesting to do is to go non-perturbatively the ability of phase slips, which we didn't do yet, but it's probably doable. And another kind of open-ended question is that if one accounts also for the for the phase slips in the array, then there is an interesting question about the interaction between the multi-photon states in the array, and that's kind of towards the possible many-body localization of plasmons. But this is kind of open and very much speculative at this point. So with that, I'll stop and thank you.
Thank you very much for this interesting talk. So we are open for questions. Okay, so in the meantime, I can ask a question. How do you, or do you have any way to control the parameter K in the experiment, or is just a fitting?
Right. So actually, with K, it's relatively easy because, yeah. So K, let me go back. Yeah. So with K, it's easy because it's related to relatively two simple characteristics: the Josephson energy and the charging energy. So there are a number of experiments that actually allow to infer it. The point is that this array is very long, but it's finite. So basically, one sees actually discrete resonances, and from the resonance structure, it's like Fabry-Perot. You can tease out the parameters of the array quite well. So these parameters EC, G are easy to find.
Yeah. Okay. Yeah,
What is difficult is the phase slip parameter, because they cannot measure this Transmon disattached. It's always attached, and that makes it very difficult to measure. Parameters. It is kind of microscopic parameter, and there is very difficult to get an independent measurement that would tell what this epsilon1 is.
Okay. Yeah. Thank you. So I don't see any other questions, so maybe I can ask, how do you have in mind the implementation of this multi-photon process? How would you appear here?
Right. Yeah. So so basically, again, for series, it's easy to say that basically you make smaller, you reduce the value of EJ, and that's relatively easy to do. It's harder to increase the value of charging energy because of the size of the junction, but EJ is easily controllable by just putting more oxide onto the junctions when they prepare the array. So it is relatively easy to make an array of more quantum junctions. What Manouchian tells me that it's very hard to measure because somehow dissipation, whatever it is, not clear, but dissipation becomes high, and the Q factor of this whole thing kind of becomes low, and they have hard time to basically to distinguish between different modes. Maybe actually this is the result of generic interaction between plasmons. I don't know, but they don't see much. The problem is they don't see much. So that's basically their early experimental paper, which I have not much to say about.
Yeah. Okay. Thank you so much. I know there is a question by Matthew. Oh. Please go ahead.
Hi, Leonid. Thank you for a great talk. I just have a really dumb question right at the very beginning, where you were modeling a single small Josephson junction and arguing that it's actually an insulator. That's presumably not the case if both sides of the junction are coupled to leads. Because this form of the EC. Yeah, anyway.
It's not a dumb question, it's a pretty serious question. But the thing is that now, if you attach it to the leads, then it's hard to define, say, what capacitance is at zero frequency.
Yeah, I got it.
So that's the problem. So basically, if you want to be mathematically consistent, you have to look at the system. And then you come to a bizarre conclusion that shunting it with a normal resistor, you make systems to be superconducting.
But so in that picture, those blue rectangles are supposed to be small superconducting islands. Is that right?
Yeah.
Okay. That's I'm good. I'm good then. Thanks.
Yeah. Thanks for this question.
Okay. Thank you very much again.